I'm pleased to open our second day of this conference on information in the sciences. This day will be dedicated to information in physics, and our first speaker, sorry? Here, is this okay? Yeah. So our first speaker this morning is Professor Olimpia Lombardi from the University of Buenos Aires. She's a principal investigator of CONICET, which is the National Council of Scientific and Technical Research, also a professor in charge of the area of philosophy of science at the Faculty of Natural Sciences. And her fields of interests are philosophy of physics, particularly quantum mechanics. And she also worked somewhat on philosophy of chemistry and biology. Professor Lombardi wrote several articles on the notion of information, on Shannon information and on quantum mechanical information, and was recently a guest editor of a special issue of the journal Entropy on information, meaning, and interpretation. So I'm pleased to open this session, please.
Thank you, Orly. Thank you, Nir, for the invitation and the great organization. I'm very happy to be here. Today, I want to talk about the work we are doing during the last 3 years about information. Even if I worked about information before, during the last 3 years, all of my group, we were working on this subject. So I want to share some of the results we obtained during these years. And the work is directed precisely on the concept of information, to try to elucidate the concept, a very elusive concept. So the content of the talk will be the following. First, I will begin by distinguishing different approaches to information and different contexts, and I will focus on the communicational context, and so then I will try to characterize that context. And in this context, I will distinguish two traditional interpretations of information with their features and their difficulties. And then I will present and analyze the deflationist view of information that is very popular now, that tried to come to replace the traditional views. Following with this background, I will talk about quantum information as defined in terms of quantum sources, or then information as defined in terms of how it is encoded, and then finally I will make some conclusions. The first part, information can be approached from two viewpoints, the semantic approach and the statistical one. The semantical one, I think that this was the approach in many talks yesterday, when we say that A has information about B, and this means that A means or represents B. So information is something that carries content, in particular semantic content. In the statistical approach, we are interested in the statistical properties of a system or the statistical correlation between systems. So it is independent on the content, in particular on the semantic content. So in this talk, I will focus on this kind of information. Second, in this approach, we can distinguish at least two big contexts. One is the computational context, and the other is the communicational context. In the first one, information is something that can be computed and can be stored. So in this context, the magnitude, the traditional magnitude, is algorithmic complexity. So it's or informational Kolmogorov information also is known. In the communicational context, information is something that can be transmitted between 2 points for communication, with the aim of communication. So in this context, the magnitudes are the informational entropies. I mean, the Shannon entropy, the von Neumann entropy, these are the Shannon theory, the Schumacher formalism. We will see them a little bit later. These are the formalism in this context. And I will focus in this context to try to elucidate the concept of information. So I will try to begin by characterizing the communicational context. What does it mean that we have communication? We have to have a source, a destination, and some correlations between source and destination. And this, we have communication when we perform certain action at the source, and this modifies the state of the destination in such a way that the state that occurred at the source can be identified at the destination. We can know what happened at the source by looking at the destination. I'm using a epistemic language, but it is not necessary. But the idea is this. So we have the source is characterized by certain states with their probabilities, the same of in the destination, and the correlations are given by certain conditional probabilities. So in this context, we can define the entropy of the source, the entropy of the destination, and the mutual or trans-information, mutual information or trans-information. The idea, well, we have also, that is very important, we have also equivocity and noise. And equivocity is the information produced at the source, but cannot be obtained, recovered at the destination. And the noise is the information that arrives at the destination, but was not produced at the source. So this is a very clear sketch. Is not, these are not sets. This is something to understand that which are the relationships between the entropies of source and destination, the mutual entropy, equivocity, and noise. And these are the relationships that can be easily seen from here. And even if we will not focus on that, I want to show that equivocity and noise can be computed with these probabilities. So this is very general, and in the ideal situation, we have a one-to-one correlation between the states of the source and the states of the destination. In this case, we say that the situation is deterministic. But this is not generic. This is the ideal situation. We can have a situation with noise or a situation with equivocity. And I would like to stress that it seems to be symmetrical, but it's not, because with noise, we can identify the state of the source by knowing the state of the destination. Even if one state of the source is correlated with two states of the destination, by knowing, by means of this one, we know which was the state of the source. It's clear. On the contrary, when we have equivocity, the state of the destination gives no, cannot say which was the state of the source. So The situations with noise are less serious, and in general, communication engineers try to design filters for noise to recover information. So the situation is not symmetric, but there is some asymmetry in communication, because, and the fact is that source and destinations are not the same. There is some asymmetry, necessary asymmetry in the communication, So now we have a clear formalism, so we can think that now we know what information is. Nevertheless, there are different interpretations of information, even within this formalism. The classical interpretations are the epistemic and the physical. According to the epistemic interpretation, information is something that supplies knowledge in certain way. For instance, McKay says, we have gained information when we know something now that we didn't know before. Or Dretske says, information is a commodity that, given the right recipient, is capable of yielding knowledge. So the idea of knowledge is always there. And I would like to stress that not only philosophers make this kind of link between information and knowledge. If you read some textbooks written for physicists or for engineers, you only find many claims, many definitions or characterizations of information in terms of knowledge. And even in papers of physicists, you can find when they say, we can take information or obtain information from a system that is knowledge from the system. It's very, very common. The other interpretation is the physical, according to which information is a kind of physical item that can be generated at one point of space and transmitted to another point of space, and that can be accumulated, stored, and converted to one form to another. This is very, well, when we say something like this, we can easily think about energy. For people, for defenders of the physical interpretation, sometimes, not always, information is something that has the same ontological category as energy. For instance, well, the traditional defender of the physical interpretation is Landauer, when he says information is physical. And there is a very well-known dictum that no information without representation. This means that there is no information without a carrier, without a physical substratum on which information is carried. But none of both interpretations are free from difficulties. The epistemic interpretation, for instance, if we think that information denotes knowledge, let us suppose that we accept that for the entropies of the source, the destination, and the mutual information. But what happened with equivocity and noise? Do they represent knowledge? Well, if we say yes, it sounds a bit strange, because something that it's an obstacle for communication denotes knowledge. Doesn't sound very reasonable that precisely what is an obstacle for communication is something that denotes knowledge. So we can say, well, no. The only magnitudes that denote knowledge are these three, and these two not. These do not denote knowledge. No. But now, it sounds strange that we can make mathematical operations between magnitudes that denote different things, something that is not allowed in physics. We sum or make subtraction of magnitudes, they have to denote the same thing. We cannot sum velocity and position. But there is another problem. Let us suppose that I have a transmitter and do two TV sets, receivers TV sets. And the transmitter transmits to the two TV sets that are in the same channel. So I can know what happened in the other one by looking at my TV set. So even if there is no physical link between the two TV sets, one can know what happens in RB by looking at RA. Even if, look at this, even if RB is later than RA, I can know what will be the state of RB later. So if I take an epistemic interpretation, I have to accept that there is a link, informational link between the two TV sets. And this is something that was said. For instance, Dretske says, from a theoretical point of view, the communication channel may be thought of as simply the set of dependent relations between S and R, in this case it's these two. If the statistical relations defining equivocation and noise equivocities, in our case, between S and R are appropriate, then there is a channel between these 2 points, and information passes between them, even if there is no direct physical link joining S with R. I mean, for somebody who takes an epistemic interpretation of information, there is a communication channel between them. The problem is that this is sound strange too, because nothing can be done here to modify the state in the other one. So if we suppose that communication, this is a completely symmetric situation, and we said from the very beginning that communication is something asymmetric. So nothing can be done here to modify the situation here. So in what sense we can say that there is communication between RA and RB? There is no communication even if there are correlations. I mean, correlations can be enough to give knowledge, but they are not enough to represent communication. What happened with the physical interpretation? The physical interpretation is the interpretation that have in their minds physicists and especially communication engineers. And this worked very well up to the moment that we found some kind of situations coming from quantum mechanics, in particular teleportation. I will say it very fast. In teleportation we have two particles. The particles are entangled, and each one of the particles, one is taken by Alice and the other by Bob. Alice makes an interaction between her particle and state phi, and then sends 2 bits to Bob in such a way that, depending on the 2 bits sent, Bob makes a kind of procedure, and he recovers the state that, and the state disappears from Alice, because I don't know if you know that quantum states cannot be cloned. So here, it seems that there is something that is transmitted from Alice to Bob, but this state cannot be sent. There is no physical channel other than the 2 bits here, but the 2 bits cannot carry all the information of a quantum state. So the question has been, how does the information go from Alice to Bob? How does information get from Alice to Bob? One very strange answer is that given by Penrose when he says, the only other link between Alice and Bob is the quantum link that the entangled pair provides. In space-time terms, this link extends back into the past from Alice to the event at which the entangled pair was produced, and then it extends forward in the future to the event where Bob performs his operation. There is no other physical connection. It is clear that he's looking for a physical channel. He's thinking on information from a physical interpretation. So he's looking for the physical channel, the physical link between source and destination. And this is very strange, a channel that goes to the past and then comes to the present. Another position is that of Deutsch and Hayden, who said that the quantum information is traveling hidden in the classical bits. These are problems for the physical interpretation. This kind of situation, like teleportation or entangled, usually called entangled assisted communication, lets physical interpretation to some artificial solutions. So now the physical interpretation has to face this kind of situations. So if both interpretations have difficulties, now the popular interpretation is the deflationist view, which absolutely cuts the Gordian knot. So by saying that there is not a question of information being a substance or an entity that is transported, nor of the information being a referring term. It seems that information is not a referring term. It seems that information is something completely abstract. Let us see what does it mean. The dictum of the deflationist view is that information is an abstract noun. For them, for him, because in general, who proposed this is Christopher Timson and is followed by several people, in particular by Armand Duell. For them, the goal of communication is to reproduce another token of the same time as that produced at the source. For instance, Timson says, if the source X produces a string of letters like the following, that one, say, then the type is the sequence, is that sequence. We may name this sequence 17. The aim is to produce at the receiving end of the communication channel another token of this type. Not the token, or what is transmitted is not a token, but types. Since types are abstract, information is abstract. So this is the essence of the argument of the deflationist view. But the problem is that source and destination can be systems of very, very different nature. For instance, my source may be a dice, and my destination may be a set of lights. And I will try to turn a light depending on the number of the dice. In what sense they are tokens of the same type? I mean, the relationship type token is a very traditional relationship of philosophy that began in philosophy of language, and that that is very discussed. For instance, some says that it is the relationship between an universal and the individuals, or the kind of the members, or properties and its instances. But I really don't see how a dice and a set of lights can be in some philosophically meaningful way tokens of the same type. So it's very strange. I think that with time, Simpson himself began to be aware of this point, because in 10 years later in his book, he says that the basic idea is of a pattern or structure, something which can be repeatedly realized in different instances. Oh, okay, now it looks better. So, the states of the source and the states of the destination, he says, they have to be the same structure. I mean, the point is sameness of structure, or we can say isomorphism, or, as Wells says, one-to-one mapping. Okay, this is better. Nevertheless, this is completely formal relation. This is not the relation between types and tokens. If the relationship between types and tokens were a formal relation of one-to-one mapping, so, for instance, there is an entry in the Stanford Encyclopedia of Philosophy online devoted to types and tokens. We can delete it, because types and tokens, the relation between tokens of the same time is a relation of isomorphism. But this is not the case. I think that a type must have some content to identify its tokens. So what I mean is that this is better. Nevertheless, this means that we have to abandon, let aside the idea of tokens and types, and this is not what they have said, they have done. But there is another problem here. The fact that communication is not always a one-to-one mapping, as we saw before. Communication with noise is not a one-to-one mapping, and nevertheless, it can count as information, communication. So they are forgetting the more realistic situations of communication, which are situations with noise. So my conclusion up to this point is that information is something very abstract, really, much more abstract than types, and my sense, I will not develop here, is that information is a formal concept that acquires content when, as any mathematical concept, acquires specific content in each one of its applications. So I have a pluralist view of information. Now I will make a formal intermezzo, very fast. Do you remember Shannon formalism? We have the source, some message, the transmitter, a signal, and the channel, and then the receiver that turns the signal into a message, and the destination. And in the case of Shannon, the transmitter makes the coding, and the coding is a mapping of the states in strings of symbols of a code alphabet, and the words, the code words, have not all the same length, so we can compute the average code word length, and if we have a n message length, this is the length, the average length, and the theorem proved by Shannon is that the minimum average length is given by, is proportional to this entropy of the source. In the case of the code alphabet, is binary, so it's completely directly proportional. In the case of Schumacher, the coding is different. We map the states of the source into states of system, a quantum system, yes, of dimension d. We can make a mixture of these states weighted by the probabilities, the original probabilities, and we can define the von Neumann entropy. Well, sorry, there is a minus missing there, please. And when the states are orthogonal, the von Neumann entropy is equal to the entropy of the source. If not, it's less. So when we have messages of n letters, we have a string of states, so we can make a state of the composed system, and it is transmitted by means of L2 state systems. We can usually called qubits. Well, we want to use the less number of qubits, and the quantum noiseless channel coding theorem says that the minimum number is proportional now, not to the Shannon entropy, but to the von Neumann entropy. Okay, what is so quantum information? One of the answers is that quantum information is what is produced by quantum information source. This is Stimson again. He says that Schumacher followed Shannon's lead, considered a device, a quantum source, which rather than outputting system corresponding to elements of a classical alphabet, produces system, in particular quantum states raw, well, in the general case, with probabilities p. Okay, the idea is that, this is the usual analogy made in many texts, that a classical source produces classical information, which corresponds to Shannon entropy measured in bits, and a quantum source produces quantum information corresponding to von Neumann entropy and measured in qubits. This is very appealing because it's very, it's very analog. However, this is not what Schumacher says in his paper. In his paper, he talks about an information source A with entropy HA, and a quantum signal source. It's a source not of messages, but of signal. Do you remember that signal is something produced by the transmitter, not by the source of information? And here he computes the von Neumann information. So this source produces messages. This quantum signal source belongs to the transmitter. So this signal source, says Schumacher, is a device that codes each message AM from the source A into a signal state AM of a quantum system M. It is clear the quantum signal source is something that makes coding, not produces the message. So there is no quantum information source. This is clear. This, the Shannon Schumacher's paper is quantum coding, not quantum information. So he calls this this process from the transmitter to the receiver transposition, because it cannot be copied, so the state is transposed from the transmitter to the receiver. So I think that it should not be confused the fidelity of the transposition between M and M prime, that is computed like this, and the effectiveness of communication between A and B. And this is measured by the transinformation, the mutual information, that is maximum when the equivocity is 0. So these are two different concepts. One is transposition and another is communication. And the effectiveness of communication depends on the fidelity, but also depends on coding and decoding. If my processes of coding and decoding are not efficient, my effectiveness of communication is less. So we can say, well, okay, this is what Schumacher says, but why not? Why cannot think that this is the source and this is the destination? We can think above what Schumacher says. Well, the fact is that they can be non-orthogonal states. So the state of M prime in general cannot be identified by measurement. So it cannot say what was the state of the source. So in what sense we can still talk about communication? What I mean is that we have here two different concepts. One is communication and the other is transposition. Communication is about information. Information is what is communicated. And transposition is about a quantum state. A quantum state is transposed. If we identify communication with transposition, we are identifying information and quantum state. So the link with the traditional concept of communication is lost, and we are not talking about information, we are talking about quantum mechanics. This is my point. I mean, we can use the words the way we want, but the fact is that if we insist to use informational discourse for this, I have no difference with quantum mechanics. What happened with coding? Timson says, the coding theorem that introduced the classical Shannon and quantum Schumacher concept of information do not merely define measures of these quantities. They also introduce the concept of what it is that is transmitted and what it is that is measured. I mean, the meaning of information is given by the theorems, the coding theorems. So classical information is what is measured by the Shannon theorem. Quantum information is what is measured by the Schumacher theorem. What are the consequences? First, the theorem becomes a definition. Traditionally, we define the information of the source, and we obtain, like a theorem, this relationship. This is the definition, a proof, and this is the theorem. Now, this is the definition, now this becomes the theorem. I mean, this is not the traditional way of looking at this. Okay, this may be not so serious, but in another, the other consequence is that the information of the source is not an average anymore. We are usually we learn that the information or the entropy of the source is an average. So, if the definition of information is this one, like it's claimed, this, I mean, the information related with one state of the source is not an information, because this is the definition. The definition is here, so this is not an information. So there are no individual amounts of information. This is what Simpson says explicitly. But if this is the case, so this magnitude is not an average, because an average is an average of individual amounts. If not, it is not an average. Another consequence is that when messages are not encoded, they don't carry information. I mean, this is very strange, because a message can be encoded or not. And even if Shannon says, when these messages are encoded, coding is made by the transmitter. And we know that in original telephone transmissions, the signal was not encoded. There was only transducing between sound and electricity, but there was not a coding. So there was not information. This is another consequence. And I think that the serious consequence is that the nature of information generated at A remains undefined up to the moment we decide how we will encode it. So then if there are really two different kinds of information, this property is undefined up to the moment we decide to encode it with classical systems or quantum systems. So it does not seem very reasonable either. So what is quantum information? Somebody can say, this is a possible answer, that classical information requires a physical carrier that travels through space and needs a finite amount of time to be transmitted. And quantum information doesn't need a physical carrier. This is something that was suggested to me by Jeffrey Babb, for instance. Perhaps the specificity of quantum information is that it does not need a physical carrier. Let us see that this is linked with a specific interpretation, physical interpretation of information. But the fact is that the consequence of this is that a source would produce different kinds of information with no change in its own nature. I mean, depending only what happened later in the transmitter stage. I mean, it's something like the nature of information is decided retrospectively when the information is encoded. So, if the kind of coding to be used at the coding stage were not decided, yes, the very nature, classical and quantum, of the information would remain indeterminate, just in the previous case. So, when we say this, we can say that quantum teleportation, the traditional case, is a rather exotic example of not of communication, but of transposition process. So teleportation is a way, among others, of implementing transposition. And it is interesting that this is not what I say, but this quote of Schumacher. The question, so, is that transposition of, we have not conflated the transposition of signals between transmitter and receiver with the communication of messages. This is a message, this is a signal, between source and destination. And this, here, we have transfer of information. Here, we have transposition of states. Conclusions. For me, there are no good reasons to suppose that there are two kinds of information different in nature. I mean, there is it's better to think in one kind of information encoded in two different ways. And this does not mean that there is no quantum information theory. Quantum information theory is information theory encoded in with quantum resources, but not because it's an information theory about, not a theory about a different kind of information. The concept of information, for me, is, I said before, is neutral with respect to the physical theories. And this kind of neutrality frees any attempt to reconstruct quantum mechanics in informational terms from the risk of circularity, because there are many attempts to reconstruct quantum mechanics in informational terms. If information were quantum, we are reconstructing quantum with quantum. Well, and this also, for me, is very interesting, and it must be thought a lot, reflected on. This opened the ways towards a non-reductive unification of physics. But perhaps it's a good concept information to introduce links between physical theories, but not in a traditional reductive way. And the perspectives of our work, we are working on that, is that how we can recover a physical but not substantialist interpretation of information, not epistemic, but not thinking like a substance that travels. So we think that we can think that there is some causation between source and destination, but the problem is that the concept of causation in itself is very obscure, so we have to decide which kind of causation have to use, and we think that the interventionist view is good, so we are trying to develop a manipulabilist interpretation of information. Thank you very much. Some papers.
Thank you very much for this very clear and wide scope presentation. And we have a few minutes to take a few questions. Please, Aaron.
Please use the mic.
Okay. There is a microphone here.
Hi, I'm Aaron. Thank you very much. I don't have enough technical knowledge to follow all the details, but I think you presented a very clear formulation of something that I would express by saying, if Shannon had not been working for a telephone company, he wouldn't have called his notion information, because Bell Labs were concerned with storage and transmission of information, and so he had to talk about information. He might have talked about messages and vehicles and data structures or whatever, and he's just confused lots and lots of people, as I think you have pointed out very clearly. But I also think that right at the end, you're coming around to exactly what I was hoping to say on Thursday, that information needs to be something that can be used. It's not primarily something that's transmitted. What's the point of transmitting information unless there's something else that's important about it? And I think the importance is use, and use is causation, and control. So if I get information from you, that may stop me going in the direction that I was going in and going in another direction. Or information from my eyes will enable me to grab something that I would not be able to grab if I had not previously seen it, and so on. So I think if we go back to the much older use of information, long before Shannon, it's there in Jane Austen's book, Pride and Prejudice has at least 25 uses of the word information, but they're all about how you can get information that you can use in various ways in controlling people and setting things up and repairing damage. And I think you've ended at the beginning of that story, which is, I think, very good. I'd like to hear, at least there won't be time today, but in the future, how you develop it.
Well, thank you for your comment, because I really agree with you. I mean, I began with these two contexts, the communicational context and the computational context, because they are the traditional one. But when we accept that information is something very abstract, we can apply it in very different contexts. One of them may be cognitive sciences, for instance, or statistical mechanics, or game theory, or evaluation of hypotheses. I think that one of the merits, the advantages of the Cover and Thomas book, who was mentioned yesterday, is that they begin like this. They say, look, information theory is completely general. They began by talking about probabilities, and then in the different, they began the first two chapters with mathematics, and then we began to apply the formalism to different contexts, different domains. So in this sense, you will like our paper called something like a pluralist view about information, because it's precisely with what we say in that paper. Thank you.
Mark, please.
Thank you very much indeed for a wonderful talk. So I wanted to ask about the criticism of Chris Timson's deflationist view on information. So one way of reading the deflationist view is that it's fundamentally a negative claim. So the claim is that it's a mistake to think of Shannon information as some kind of substance that sloshes around like water or a fluid or any kind of thing which is actually physically transmitted between one point and another. And if you do think along those lines, so if you do think that it is something that's sloshing around between the sender and the receiver, then you start looking for some physical mechanism that can support that, and that seems to be absent in the cases of the two televisions and also in the quantum case. So you get into a massive puzzle. So the main claim of the deflationary view is that it's just a mistake to think of information in those terms, and that there's nothing in the Shannon's formal definitions, nor in the motivation, the informal motivation behind Shannon's definitions, that would compel you to think of information in those terms. So I was just trying to square that with the criticism that you mounted of Chris Timson, because it seemed to be that a lot of what you were saying was compatible with that overall deflationary view of information.
Yes, in a certain sense, my position is also deflationist. My point against Timson is not the conclusion, but the arguments he used to arrive to his conclusion. This use of types and tokens that is very, very repeated in the literature. But I can agree with the conclusion.
So, yes, please.
Whether procession is the act of cognition, is developed, arrives in order to know something because of procession.
So my English is terrible, but I cannot understand. I'm sorry.
Yes,
Yes, very bad.
The matter of procession, whether it is the subject or the element of knowledge or of discovery.
I'm not sure that I understand myself. The matter of what?
Well, in procession, we have the matter. Whether this matter introduce you to discover some other matter, some other element for knowledge.
Well, if I understand well, I'm not giving some discovery or some new formal result. My work is a work of philosophical elucidation. If I understand your question, I mean, I'm not, or we, because this is a work of all my group, we are not finding new theorems or new results, or new algorithms or like this, but we are making a very, very philosophical work of elucidation of a very controversial notion, if I understand well.
Thank you very much.
Sorry, with my ear in English is...
Okay. We have time for one more question, so either... Yes, so please.
I mean, I think that for most...
Here, I'm sorry.
Yeah, I'm more familiar with the epistemic meaning of information, and the physical one seems a bit unclear, but you suggested something at the end about causation. Maybe you can say something. You really believe that it can be more than epistemic? I mean, I understand that the deflationist approach is also pushes towards epistemic, right? So do you suggest a really physical interpretation?
No. Thank you for your question, because it's interesting to be clear, well, about my position. I'm not saying that it's the right one. But I think that if we want to recover a physical view of information, we need causation. Nevertheless, when we consider information from a very abstract viewpoint, the physical interpretation is only one of them. And perhaps the epistemic is another one, and it's useful in another context. And perhaps the interpretation in game theory is another one, and it's useful in that context. I mean, for me, going back to the first question, since information is very, very abstract, it can be used in different contexts with different interpretations. Interpretations in the semantical way. I have a formalism, a formal concept that I give different denotations in different contexts. But if I want to use it in the physical context, then I have to use some concept of causation. But it is not, I don't mean that this is the right way of thinking about information, the physical one.
So thank you very much for this talk.